All right, good. So there's the Zoom, and I see a few people are coming in. Okay, so today, let me go to 123 and the schedule. All right, so today is
Hello.
7. Let's see, I better put this forward. If you already know programming, this will all be pretty easy, but there are a couple of things about the security implications. So let me just put up here today. Project 9 and 10 due. And next week is 317, Chapter 8 quiz, and Project 11 and 12. Okay. By the way, I noticed this morning that the quiz, this particular quiz was taking the average of your 2 attempts instead of the highest, and I fixed that right before class. So a few of you sharp-eyed people might notice that if you took it for 16, took it again for 20, you actually had 18, but we changed it to 20 about an hour ago. So let me know if anything like that happens and you spot it. I make an extraordinary number of mistakes in Canvas. Anyway, so let's talk about programming. And by the way, if you really want to learn programming, there are, of course, a bunch of classes over in CS where you can really learn real programming. And real programming is pretty irritating because you have to think of everything and you have to spend a lot of time chasing exceptions. You have to consider every possible thing that could go wrong and handle it correctly so your program doesn't crash. And the kind of programming I'm going to talk about here is what security professionals need to know. You are not usually a developer. Developers spend most of their time learning how to make things fast and efficient and small and bulletproof. But what they mean by bulletproof typically is what Microsoft did until 2002. We were talking about this before class, which is make code that works when a normal user tries to get their job done. Not code that will survive deliberately evil, malicious attacks. I was just talking to her before class. People are saying, we don't need to worry about someone putting 5,000 characters in the password field. I say, a normal user wouldn't, but the attackers would. Yeah.
Well, when I test, I take 2 points of view, the evil person and the clueless person.
Yes. That's an evil person and clueless person, and that's it. Microsoft's official position until 2002 was you only need to worry about the clueless person. A normal person trying to get through the day doing their job, that's what we want. We want software that will work in the office all day long without crashing. But an evil person deliberately trying to make it crash, we don't need to worry about that because that's not happening very much. But in 2002, that was happening so much that Microsoft could no longer deny it, and they started making software that could withstand real attacks. So our interest here is not to teach you how to really do programming, which is of a professional character, but show you the common programming mistakes that lead to security problems and how to hatch them, which is what you would need not to be a developer, but to be the security reviewer at the quality control stage of software to notice what the developers didn't put in, which is typical because most development training programs, and in fact, virtually all of them, do not teach them anything about security. So they create generation after generation of programmers that keep making the same mistakes over and over, which is kind of nuts, but that's the way it is. So we'll talk about the basic concepts of programming and make some simple programs to demonstrate the problems. C is the source of most security problems, and we'll talk about this. PHP, by the way, causes a lot of others, and now Amazon is racing to the top of causing god-awful security problems because if you store data on Amazon E2C by default, it's available to the whole world. And an incredible number of people do not know that, and so their private data is just blowing in the breeze. And Chris Vickery and other people are energetically finding huge data repositories of supposedly private data there. But anyway, but most of the security exploits came from C because C is dangerous. C is like driving a car without any real controls where you're sort of reaching in with wrenches and adjusting things in a running motor. It's very fast and very efficient if you're an expert, but you have to be careful. It places a large burden on the programmer to be careful, and many of them are not able to be perfect at always remembering the various things they're supposed to be considering when they code. So here's a good quote about this. Programming is easy like riding a bike, except the bike's on fire and you're on fire and everything is on fire and you're in hell. It's just the way it is. I mean, all a computer does is exactly what you told it to do. And that sounds great until you find out how much you didn't really consider what you were saying, just like when someone gives you 3 wishes. And you wish for $1 million, so your parents die. Now you have $1 million. Are you happy? Hey, wait a minute. That's not what I wanted. Well, that's what you asked for. You shouldn't have asked for that if that's not what you wanted. Anyway, all right. So here's the rules. You have to write this code, which has to be inhumanly perfect at the moment, although people are talking about AI coming in and assisting programmers to write better code. And at first that will of course make everything even worse, but in the long run, it might make it better. But anyway, so when you write code, you make mistakes, and then you find some of the mistakes and some of the mistakes you don't find. So all computer programming code is full of mistakes, just like everything else, just like your car and the pills your doctor gives you and the medical tests they give you. Everything is not perfect. There are mistakes in it, and you just cope. So the fundamental concept of the thing called computer programming is a language is a programming language if it has these three features: branching, looping, and testing. And that is what makes it what is mathematically and philosophically called NP complete. It can solve a certain category of problems, and those problems are the ones that can be boiled down to an algorithm for a series of steps. Do this, do this, do this. There are some problems that cannot be boiled down to an algorithm like that, and there is currently a huge argument about whether computers can solve those problems or not. So in the early days, we all wrote spaghetti code in languages like Fortran 4, where you just use go to and jump down here and jump down here, and the actual flow of passing through the code was just a mess, and that turned out to be very hard to maintain and improve. That's what I used to write years ago, like in the 70s. What worked better is to have structured code where you make a little function that does one thing and another function that does one thing, and you test them, and then your main program just calls this function and that function. So you break things up into small modules that can be independently written, and this works better when you have a large team of programmers. One person writes one module, or one team, another team writes another module, and then you can reuse the function in a later program without having to rewrite it, and that turns out to be the best way to get it done. So branching moves from one part of the program to another. The original way was with a go-to statement that was considered very miserable to maintain, and they switched to what you should do as a function call statement, where you call a function and it then returns when it's done. That's a lot more organized and easier to live with than go-to. Looping is doing something over and over until some condition is finished, like for I equals 1 to 100, do something. And testing is some kind of test that returns true or false, and then you take the output of that, and you may do something, print a different statement depending on whether it's true or false. So let's get these things going. Let me put up a simple program here. I'm going to do them in the latest version of Corley. Corley, by the way, is not intended to be a development environment. You can do some of it, but it's intended to be an attack system and not really designed for development. So, but you can do a little development in it. If you actually, yeah, typically use Ubuntu. Ubuntu is the most popular, or Mint, or Red Hat. Those are the systems that are really designed. If you're actually running a server that is serving up data to somebody, you wouldn't run Corley. That would be crazy, because it doesn't have what you'd run is Ubuntu or Mint, Red Hat, SUSE, that sort of thing. That's what they're designed for. And they're not primarily designed for security. So if you try to like hack with that, you're going to have to install these codes and libraries. Corley's an attack system. That's why Amazon now offers Corley as a platform for cloud machines. And I just went to the training. If you turn on the Amazon protection features like Guard Dog, one of the top 10 security risks it will find is somebody used Corley. They give it to you, but if anybody's actually using it in your company, you definitely should be warned about that. If someone's using Corley, it better be your security team. If anybody else is actually using Corley, they're way off track, and you want to stop that. You should not be serving web pages from Corley or surfing the web, reading your email in Corley or anything. It's not intended for that. It's not safe. It's an attack tool. It's not expected to do productive forward things. It's a breaker, not a maker. Anyway, so here I'm in Corley. So I'll go to 123. And let's make, I don't think I made anything yet. Okay, so I'm going to make this program here just to get us going. And then I can talk about the fundamental concepts of C. So let's use Nano, which is a very primitive text editor, but the one I recommend getting used to. Unless you're cool enough to learn VI, which is even cooler, you want to learn a text-only editor, because often when you hack into a machine, you don't have graphics. And you shouldn't be helpless without graphics, so it's good to stay reasonably in shape to use it. Nano is the wimpy text editor. The pros use VI, which is more powerful, but more irritating to remember unless you use it a lot. So I'm going to make what? Hello.c demo. Okay, demo1.c. So I include a library, the standard IO. You almost always need that. And that means it's going to link to a precompiled library that somebody else wrote. And I'm just going to print hello world and put a carriage return at the end of it. And I already made a mistake. All right, that should be a \n for a carriage return. Okay. In fact, let's make another mistake. If I forget to put in the semicolon, let's see what happens. By the way, I'll get rid of the colors, which might make this better to see online. Okay, so there's an attempt to write a program, which is wrong. You compile it with your new compiler. So GCC, put the output in hello, and take, or not hello, but demo, and put the input from demo1.c. Okay, that'll compile it, and now I get an error. If you get an error, your code will not run. It's refused to compile it, and the problem is I'm missing a semicolon. This is why programming is so difficult. You have to have inhuman precision. C requires you to have semicolons at the end of every line, and if you don't succeed, it won't work. This kind of error is relatively unimportant because the compiler warns you and you can't proceed without fixing it. But you can make more subtle errors, like I was supposed to use variable I, but I accidentally used variable j. That led to a blue screen of death in Windows Vista. If that kind of mistake, the compiler can't catch it because there is a variable called j, and for all it knows, you intended to use j, but that leads to some sort of disaster because j doesn't contain the data you expected. Your computer can't detect that. Only your humans testing it can detect that, and they often don't. And so you end up with code that doesn't work. So now I compile that. Now I get a warning telling me it would have liked me to specify that main was an integer, but it made up a default value. So now I can run, it will run, and it prints hello, and nothing bad happens. So that's fine. Now you have to compile it. This is high-level C source code, which is more or less human readable. You can't run that. The processor only knows machine language. You have to turn it into machine language, and that's what this stuff is, and that's why it's so much bigger, 7 kilobytes instead of 50 bytes. It had to add a whole bunch of extra stuff to it, and if you want to write that, we're doing it in 127 class where we write assembly code and look at the assembly code. It's baffling at first, and you get used to it. But everyone prefers to write in high-level languages because a couple of lines of high-level turn into thousands of bytes of assembly language. So it's much more efficient to write in a high-level languages when you can. But you don't have complete control over the output. Different versions of the compiler will make different assembly language. It's like driving a car in automatic. You're not really controlling exactly what it does. But it's easiest to just get where you're going if you don't really need to control all the details that way. So you can put in comments. One way is with this /* and a */ at the other end. You can put in comments that say what your code is doing, and this is very helpful. Most professional developers are forced to have extensive commenting of their code so that other teams can read your code. There's a lot of online cartoons that are funny about this. There's nothing sort of more horrible than trying to fix somebody else's code because you can't even figure it out. It's usually much better to just throw it away and write it yourself from scratch than to try to figure out what someone else is thinking. That's why one of the most difficult things I do as a teacher, a student comes to me and say, here I am on step 50 and my homework project is not working. I'm like, okay, you went wrong many steps back. You know, it's an interesting challenge, but it's much more difficult to take somebody who has gone way down the wrong path and find out what happened than to just do it from the start, right? Like I remember, that hasn't happened in the latest semesters, but in my previous semesters, the #1 most common problem with homework is people would skip step 1 and they would use the wrong operating system. They're trying to use Windows instead of Linux or something. And of course, nothing works. It's all very baffling, but there's often a thing like that. So here's branching and testing. So you can input a number. Now, when you input something, this is one of the things about C. You have to tell it what you're going to get. So I'm telling you, I'm going to get an integer called age. And then I put it on a message, then I scan it. I have to tell it that that's an integer. You have to tell, I'm going to read a value and I'm going to store it somewhere. You have to tell it where to store it and how big it is. Then you read it. If age is greater than 0, it prints something. Otherwise, it doesn't print it. Now, the important thing about this is this function call. So I have a routine called main. Then I hit this line here where I call printf. That means it has to stop executing lines in main, remember where it left off, go down and execute this subroutine called printf and print something. And when it's done with that, it has to return back to main, which means it has to resume what happened. This is like you're reading a book and the phone rings. You put down the book, you handle the phone call. Now you come back and try to resume reading the book, remembering where you were. And this step of coming back is very dangerous, and that's how you typically take over a machine. You subvert this step so that when it tries to resume operation in main, it instead goes somewhere else and runs the code you put in. That's how the most common attacks work. That is what makes structured programming so useful, that you have these subroutines, but it also creates a vulnerability, which you can exploit if you can somehow trick it into misunderstanding how to pick up where it left off. Because it had to store where to resume. And you can find where that's stored and change it. So then there's looping. And this one here is fun. Let me put this one in because this is your first sort of quiz thing, loop. This is a very common kind of error, easy to understand, but hard to avoid. So let's include standard IO, headers again, and then main, and this, and now int I. By the way, you don't need to put in tabs or anything because C doesn't care about white space. That's why you need those semicolons. It doesn't really care about tabs or spaces or anything. Python does. This really frustrated me when I started using Python. Spaces and tabs matter, and I was used to C. I was very baffled why none of my Python would work. But anyway, so 4. So here's how you make a loop in C, which is a really bad idea in case you're interested. There used to be a very primitive language called BASIC that I used in the 70s. And you make a loop, you just said for I equals 1 to 10. Do something next I. That was easy and it worked fine. And I don't know why they don't do that in C. This is what they do instead. And you're going to see why I hate this. Although it does provide employment for all of us. Because it's one of the many things about C that just tempt you to do it wrong. Okay, print F. Hello. Okay, and then we're all done. Okay, there's my program. So here's a fun question. How many times is this going to print hello? 10 is what the programmer intended. Let's see what happens. GCC minus, I think the answer is 11. Let's put the output in loop, and let's put the input from loop. Okay, it compiles. Now if I run loop, I got to spell it better. Okay, there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is called an off by 1 error. It's one of the very common errors in C. And what happens is, the way it works is, it starts with I equals 0 and then executes this. Then it increments I. As long as it's less than 11, it does it again. So it does it for 0 and it does it for 10. So you intended to do something 10 times, but you really did it 11 times. This is off by 1. This may seem like a small problem, but it often is big enough to take over the machine. Because you were supposed to limit input to 100 bytes, but you let me put in 101. And that 1 extra byte let me overflow the end and add all kinds of more stuff. This is one of the more common vulnerabilities. And there's 3 or 4 things that happen in C that make a hole big enough to take over the computer. And that's one of them, the off by 1 error. So an algorithm is the rules. Remember I said all computer programs can solve these so-called, I think they're called the P problems. Ones where you can write down a list of steps. Where if you do those steps, you get to the answer. Computers can certainly solve those problems, and those are the only kind we mostly do these days, although we're slowly moving into machine learning, where the machine figures out for itself how to do something without a human telling it how. By the way, there was a video that came out a week ago. It was awesome. There's an old game called Qbert where you jump around, and they got an artificial intelligence to play Qbert, and it found a bug in Qbert that no human player ever found, so it could win. And I got the original Qbert developers to say, no, that's totally not right. There's some way to hop around in a certain pattern that causes it to like give 1,000 points every time you hop from now on. So that's what AI is supposed to do. It's supposed to be able to learn and think of strategies humans did not think. And pretty soon we'll have AIs winning at chess and Go and everything the same way by thinking of strategies that no human ever thought of. Anyway, so bugs are mistakes that cause some unexpected results, and pseudocode is how you start planning. A beginning programmer will jump right on the computer and start typing code as soon as you give them a problem. A professional programmer will spend 80% of their time planning before they write any code at all. Because you learn the hard way. Just like, here's another fun fact. I don't know about you, but I lost my thesis 6 times before I learned to back up. And I think this happens to everybody. You forget to back up stuff because it's too much hassle until you lose it enough times that you learn it's really not too much hassle to back up my stuff. And in the same regard, you only have to write a certain number of programs only to discover that your fundamental idea was wrong, to realize you really should plan what you're doing first before you write. because you could very well be writing nonsense you're going to have to throw away. Anyway, so here's the pseudocode for shopping. Purchase ingredients. Purchase ingredients is one thing I have to do. That's going to call subroutines. You're going to call get car, unlock the garage, start the car, drive to store, purchase these items, end to purchase ingredients. Now we can go on to like chop up ingredients and heat up the stove and other functions. This is how you think. You think of everything that has to happen and what order it has to happen. And then when you write code, you write one little module that does one thing, like get the car. And then if you want to go somewhere else, you can use the same get the car routine that you wrote for some other purpose. So you have to document everything. And if you're at a professional shop, your documentation has to meet a certain format and be very thorough and be online so other developers can read and decide whether your function is going to work for their purpose or not, and exactly how to use it. This is annoying, like doing your taxes. It's not as much fun as coding, but it's essential if you want to write code that works. So the industry standard is 2 to 3% bugs, which is pretty horrible. If you think about it, Windows 2000 has much less, one per 1,000. Linux has 6 times less, 0.17 per 1,000. And these are for old products where the source code became available in Windows. So Linux source code is always available, but nobody has 0 bugs. And every single bug could lead to total system compromise. It's very annoying. This is why a lot of people have been very upset as the internet becomes more and more important. We are all trusting something that is intrinsically very risky. All of us are using defective hardware over a defective network to connect to defective hardware at the other end, and there's defective software at every step too. So it is not too surprising that everybody and their brother is getting hacked. So C was developed by Dennis Ritchie at Bell Labs. It was funded as a government project, so it became free to the world. It was very important because before this, mainframe computers could not talk to each other. When I went through grad school, one of the guys in my lab got a PhD just for developing what was essentially a modem. Something that would make it possible for one mainframe computer in Ohio to talk to another mainframe computer in Illinois, because there was no way to do that at that time. There was no internet, and all the computers were different. You could buy a computer, and it would be an IBM, and you'd get 5 phone books full of IBM manuals. And if you bought a VAX, it was 100% different, and you had to learn it. So they said, this is for the birds. We need a unifying language. They invented the operating system called Unix, which was going to be the same on every piece of hardware. So now they could all talk to each other. And in order for that to work, you had to write C, which was the language to write Unix in. And now all you had to do is write a C compiler for each brand of computer. Then you could use the C compiler to put Unix on it. And now all the programmers could just use Unix, and they didn't really need to know or care what kind of hardware they were using, which was a giant leap forward, eventually leading to the internet. C++ was the enhancement of C to go to object-oriented code. C is very fast, very powerful, and very dangerous. C is very close to writing machine code directly. So assembly language looks like this. You have public start, proc, near, push, push, call. Each command just moves 8 or 16 or 32 bits around from one place to another. It takes thousands of commands to do something simple like open a Word document and display it on the screen. And so nobody really wants to write assembly language. You want to write a high-level language and have the computer write the assembly language from it, and that's what most people do. But if you want to hack into machines or really get to the bottom of exactly how they work, you have to use assembly language. So the compiler is the program that turns your machine, your human-readable high-level language like C into executable binary code. And by the way, Ubuntu Linux doesn't even come with a compiler anymore because most people just want to use it. If you want to compile, you have to install this thing called Build Essential, which puts on a C compiler, and so you compile things with GCC. So here's the C program. There's your comments. We talked about that. The include statement includes libraries. You almost always want to include libraries so you don't have to write everything. You include some standard library to do boring things like take input from the user and put output on the screen and so on. You write functions that call other things like the printf function. So curly braces are the start and end of a function, and it has a name up here, and in the parentheses are arguments. Every program has to start with a main function, every C program. That's how the operating system knows where to start. When you double click on an icon or you type the name of a program, it looks for the main function, and that's where it starts. So functions can call other functions. And you have to declare the variables. Like I said, you cannot just put something in a variable the way you might in Visual Basic, and the computer will figure out how much room to save. You have to tell it how much room to save, and it does not check to see if you make a mistake. There are a lot of variable types. There's integers, floating points, double precision, characters, strings, logical variables, lots of different kinds of variables. Plus plus here adds something to a number, so that's the loop that does 11 times instead of 10. And you've got a lot of math operators. You can do everything. You've got modular arithmetic and division and multiplication and binary math, and every kind of mathematical operation is available to you. And you can do logical things like I less than 11. That's a logical comparison, and the result is either true or false. And in the context of a loop, it will keep looping as long as that condition is true, and it will stop looping when that condition becomes false. And so you've got equals equals, because a single equals assigns a variable a value. A double equals compares to produce a logical result of whether they're equal or not. And you've got not equals and less than and greater than and other options here. So let's make a vulnerable program and crash it. So I want to read in a name. Let's call this hello.c. Bring in my library. Okay. I don't have to think yet. I need one of them and I need that. Okay, now I make room for a 10-letter name, 10 characters. Then I print something. Okay. Then I scan into the name, calling it a string. %s means interpreted as a string. Read in the value of the name, and then I print out the name. Printf hello %s/n name. Okay, so that'll read a name, save it someplace, and then echo it back to me. Let's see if that works. I gcc, put the output in hello, and take the input from hello.c. I get a warning, but not an error, so it did compile, so I can run it. And once a name, I put in Sam, it says hello Sam. Okay, so that seems to be working. And now, what happens if I put in a longer name? It takes it. What happens if I put in an even longer name? I get a segmentation fault. It echoes it, but then crashes. Now, the reason is because I only saved enough room for 10 characters. And when I put in more than 10, a normal intelligent language like Java or Visual Basic would not let you do it. It would just reserve more room to fit the base. But here you can cheerfully say, give me a 1-gallon bucket. Yes, sir. Put 100 gallons of junk in it. Yes, sir. No problem. I don't think I obey orders. Because, you know, and it totally does that. So it starts at the first of the 10 items and it just writes all these, and then it runs past it and starts overriding memory that is reserved for other purposes until it eventually hits that stored return pointer and crashes. So that's a buffer overflow, one of the most common problems created by C. And this is because C places too heavy a burden on the programmer. The programmer can't just say, I want to store text. It has to reserve room, but the programmer probably doesn't know how big it's going to be at this point, so they guess. And then when they use it, they're supposed to remember how big it was and check themselves before they print it that it's not too big. And that's asking a lot of your poor programmer who has other things to worry about. A more friendly language would automatically take care of that, but C doesn't. So here's how you take over machine. You find a program that's written that way, where it has something like name of 20, but it doesn't remember to only let you put 20 in. So you put in a lot, like 1,000 characters in where it expects only 20. Now, if you just put in a lot of A's, like I did, then the program will crash. And that's a denial of service attack, and that is an exploit of a kind. But exploit development, which we're doing in the afternoon section here, is improving denial of service attacks into remote control attacks, which are more powerful. And here's how you do it. You overwrite with junk, then you find where the extended instruction pointer is stored, which is here. Because when it was gonna, if it's in a subroutine, it was gonna hit the end and return to main. So it stored that here at the end. It stored some register values to restore on the way back. So you overwrite that with a controlled number, then you keep going, then you put in an attack. Attacks look like this. You get an egg. An egg is compiled machine language that does something good, usually a remote socket. So it makes a connection back to the command and control server and lets them have a command prompt so they can execute code. You can just download these. You can make them with Metasploit. It takes maybe 50 or 100 bytes to do that. So this is the code I'm trying to execute. So I put it in the name field, and I put a bunch of NOPs before it. That's called a NOP sled, because it turns out the NOP does nothing. So if I jump to any of these addresses, like 700,150, it'll do nothing, 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 slide down the NOP sled and hit the egg, which is my exploit. So my exploit will get run. Technically, you don't need a NOP sled, but in practice, it helps because you have to figure out where this stuff is. And you have to put that address here so you can jump into it. In order for that to work, you have to be able to find out where code is, and it turns out that your test system where you develop the exploit might not be exactly the same as the server that's running that you're trying to take over. So in case it's not the same, your address might be off by something. So putting in 100 or 1,000 bytes of NOP makes it much more likely that your exploit will work, because even if you're off by some small amount, it'll still hit somewhere in the NOP sled. In the most extreme case, you do heap spraying, where you have no control over where the code goes. If they have address space layout randomization, and you can still take over machines without having any idea where your attack code went if you use a heap spray and a large enough NOP sled. But anyway, this is the fundamental attack of a buffer overflow. And we should talk about the defenses that block this. The simplest one is the one I just mentioned. If you have a Windows machine like Windows XP or earlier, it did not have address space layout randomization. So you just boot it up and it would take the first block of memory and put Windows there. Then you'd start like your antivirus and it'll go here. You'd start your web server and it will go here. You start your SQL server. It will just use the next available block of memory for every program. So you could very easily build your own Windows machine and install the same software, and you could pretty much tell where everything was going to be. So now if you find a vulnerability and you feed in code, you can pretty much find out where it is. So address space layout randomization is the defense that just randomly moves everything. Every time you restart the machine, it randomly chooses a different block of memory for each process. So you have no idea where you are. The server might have 4 gigabytes of memory, and you have no clue where you are. So now, even if you find a weakness that lets you inject code, it's difficult to find it and run it.
Does it only randomize on startup?
Yes, it only randomizes on startup. Also when you launch each process, so you relaunch a userland process. But once it starts, it doesn't move it again. It can't, because the operating system is using that code. And by the way, it has a lot of weaknesses. And one of them is Windows ASLR only has 12 bits of entropy. So there are only 1,000 possible places it can go. So one simple way to defeat ASLR is to just run your attack 1,000 times until you get lucky. And another one is the heap spray, the one I talked about, where you just write JavaScript that makes copies of your attack until you fill all available memory with copies of your attack. Then you make a really big NOP sled, like 10,000 bytes, and then you just jump at random. And the odds are pretty good that you'll hit one of those NOP sleds. So you really need to know where you're putting your code. Data execution prevention lets you put permissions on memory. This has been in motherboards for at least 10 years, but it was not implemented by versions of Windows before XP Service Pack 3, I think. Maybe it was Service Pack 1. One of the service packs added this. So you could mark a region of memory non-executable. And that's what you should do for the stack. The stack is where you have temporary storage of buffers. So you mark this area non-executable, and you can still use it for its appropriate purpose, which is you reserve place for name, you write in the value for the name, and then you read it out. When you jump in the subroutine, you write on the stack the instruction pointer to resume that, and when I'm done, I fetch it off of there and return. And now if I try to do this attack, I can do all this. I can overwrite the EIP, I can overwrite this data down here, I can put an address into my NOP sled, but when I jump in the NOP sled, it will stop. It will not execute the NOP because I don't have execute permission in RAM. This is a sure way to detect this as an exploit developer. If you jump to a NOP and it won't run, the only thing that can cause that is data execution prevention, the NX bit, because NOP can always run. You don't need any permissions. You can't. If NOP won't move, then your memory is marked non-executable. And that stops the whole category of attacks. So another one is stack smashing. This is what my Ubuntu machine just did. If you looked at the error, it said stack smashing. The way this works is you're storing, and by the way, my chart is wrong a little bit. The canary used to be before the EIP. Anyway, at the end of storing the data, you put a canary value, then you put the EIP below that. So if somebody starts overwriting, trying to hit the EIP, they also overwrite your canary on the way there. And now you can tell that value has changed, and that means you know stack smashing has been detected. And that, I didn't see it here, but I've seen it in your other versions of Ubuntu. I think if you use Ubuntu, you'll see it. I don't see it in my Corley. This one here actually said stack smashing detected. That's what it showed in earlier versions of Corley. And that's this particular defense called a canary value. And that's named after the canary in a coal mine. You take a canary in a cage and put them on a stick. And if there's bad air in there, the canary will fall over and you can tell you better not go in there. And so this will detect when somebody is overflowing variables. So those are defenses. And for every defense, there's a stronger attack that will get through it. And we're doing that in the exploit development class. But these were a huge leap forward for Microsoft Windows security. As a result of that secure computing memo in 2002, Microsoft added these defenses to their operating system, among many others, and it ended an entire generation of viruses and other attacks. And all the attackers had to improve their game and have more complicated, sophisticated attacks to get through these defenses. All right, so that's C. Enjoy that. Let me just see where my Kahoots are. I'm getting a feeling that somehow I've ended up with a slide deck without Kahoots in it. I think it's time for some Kahoots. Let me find them here. I'm pretty sure that we ought to, yeah, it's brought at the right time. Somehow I've ended up with the wrong slide deck, but we can cope. This is chapter 7. All right. Let's just try these and let me turn on the sound. Okay. All right. There we go. All right. I'm pretty sure this is the right place for Kahoots. Free. All right, let's see. Give it another few seconds. Oh, the people still coming in. Okay. All right. So what function do you not need in a programming language? All right, inheritance is a feature of object-oriented programming languages, which is useful, but it is not necessary. The earlier generations of programming languages, like unstructured and structured, were still programming languages. Inheritance gave you the ability to define a class and define a subclass that would inherit properties of the class. And while useful, that's not essential. All right. 2% of code consists of what? Okay, bugs. People make a lot of mistakes, of course. Okay, which language came from Bell Labs? Okay, let's see. Good. All right. What language is built into the processor? Okay, that's machine language. Assembly language is the slightly human readable stuff like move and call, and that is still not in the processor. All the processor does is binary instructions built in, and you can't change that unless you throw out the chip and buy a new chip. And by the way, there are bugs in the processor, 100 known bugs in the Pentium 4 and later, and there's no way to patch them. And one thing that made the government very, very nervous is you could put hardware Trojans in the code, in the chips. Your processor could have a secret extra command which says, now I'll put myself under remote control from China. And you would never know because there's no way to audit it, which is why the government issued statements. We got to quit using Russian antivirus and we got to quit using hardware from China because we're just asking for it. That could be in there and you would never know. And from previous experience with the NSA and the FBI's alerts, I've discovered a simple pattern, which I cannot prove, which is when they warn us not to do something, that's because they are already doing it to our enemies. So I assume we are sending poison chips to other countries and they are using it, and that's why they're warning us not to do it. Because when they told us to quit using USB sticks, it was because we were sending poison sticks to Iraq, and this has been true. And they told us that viruses would now destroy hardware, it's because we were doing it to Iraq, and on it goes. So when the NSA tells us to worry about quantum computers, I'm pretty sure that means they've got one. That's how it usually goes. Anyway, all right. So how many characters will that print? How many A's? Okay, yep, you got it. Does it 9 times from 1 to 9, and it quits when you hit 10. All right, good. So Louise and Forrest, these all look like real names. Good. Okay, so we should take a 10-minute break. Let's pick up at 11. Gives you about 8 minutes to stretch your legs or whatever you want to do. And then we'll carry on.
When do you get the passwords for to download software?
You have it already. So if you want to get Microsoft software, go to my page and go here. And then your username is your City College email address. And you can say, forgot your password, and it will email you a new password. So you all have access to get this software. Use your mail.ccsf.edu email address. Okay, sure. I'm going to pause the Kahoot. Someone told me I can do this without stopping the share, but maybe I can't figure out how.
Pause sharing.
You see it? Yeah, pause recording. There we are. Good. Just so, all right, I'll resume it in a few minutes. All right. Neat. Somebody came and showed me how to do this. I think it was you. I'm slightly less incompetent at operating Zoom now. All right. So, all right. So HTML is not a programming language. It is a markup language. General category of XML, extensible markup language. And the point of this is just to say how something looks. You cannot do calculations. There are no variables. You can't add numbers or anything. But it's used to make all the web pages you look at on the web at some level, although a lot of them are now automatically generated by content management systems like WordPress. So HTML, you start your code with HTML and less than and greater than signs, and you end it with a /HTML. And you use header tags and paragraph tags and such to describe how big text should be and how it should be laid out. And so you write source code that's just a bunch of plain text, and then when it's rendered by a website, it puts it in different colors and fonts and images and videos and all that jazz. So you write the source code that describes what it is, and the browser constructs this graphical environment here out of the pieces of source code that it loads. So, all right, that's the HTML itself is just for visual presentation of things. Now, there are programming languages used for websites, and one of the many ones is Perl. Perl is designed to make it easy to read structured data from a text file and break it into its components. That's what it's designed for. Larry Wall wrote it. It runs on any platform, but it's most common on Unix systems. It's considered pretty old, not considered a very hot skill anymore, but a lot of people still use it. So it has simple syntax. You can just write prints. One of the crazy things about Perl is you can run it in compiled mode, but almost everyone runs it in interpreted mode, which means it just executes the commands one by one as you type them in. Yeah. Yeah, that's what I should. Yeah, compiled code is what we did in C, where you write the source code and you can't run it until you compile it and turn it into machine language. Interpreted code, you write one command and it executes. Write one more command and it executes. So if you go to the bash command line and you type things like ls and ifconfig, that's interpreted. You give it one command, it executes it. An interpreted code does not get compiled. It just executes the source code line by line. So it has to translate each line one by one into assembly language and run it. So for example, Python, which is the main one most programmers use. If you go here and run Python, I can now just do commands like A equals 1, B equals 2, C equals A plus B, and then print C. So I get 3. That's interpreted. Every command I issue is translated to machine code and executed right away. In compiled code, that's what I did with C, where you have to write it, save it, compile it, and then run the compiled code. So it's less convenient, but it runs thousands of times faster. This is slower, but more. So anyway, that's Perl is typically run interpreted, and you have the same kind of printf that you'd have in C with these format strings to tell it whether things are integers or characters or what they are. You put a sub in front of function names. All variables start with a $ character, even though they're not money, which is kind of rude. Comment lines are with pounds, and you use an ampersand to call a function, which always gives me a headache. Very strange syntax. So you can make a subroutine called speak that will print a word, and then you call it with ampersand speak. And you put semicolons at the end of the lines. So you can build code with subroutines and such, but it looks kind of screwy. And down here, you have to put a $ in front of the word because it's a variable. So that's the joy of Perl. It turns out to be extremely powerful for handling text files and not very useful for doing math and things like that. Anyway, the for loop looks a lot like a C for loop. And this is something that will create a file full of ping commands, which you could then execute to do a ping sweep. And you'll do a few of these sort of things in the projects. So here's a condition being tested. I open info with a minus. This is how you take input from the user in Perl. Now IQ equals this bracket info. Now if it's greater than 7, it prints one message, and otherwise it prints another message. All right, so that's Perl for what it's worth. Python is what we're mainly going to use in this class and in the classes after, where we develop exploits. Most programmers, a lot of security people don't do much coding, but you need to know at least one language. And if you only know one language, it should probably be Python. Python is the easiest, friendliest language for beginners to learn. C is more difficult. Java is quite a bit more difficult. And they're worth knowing, but if you don't know anything, start with Python. Python or JavaScript is a logical first language. They're very easy to use. Perl and C++ and Java are valuable but more confusing to learn. And Perl is getting kind of old. I wouldn't do that until you've done those other big ones. Anyway, so there's a lot of object-oriented programming languages out there now which have the ability to define more abstract data structures. This turns out to be extremely useful, and almost every language has this ability now, the modern ones. So you have this thing called inheritance. So I have employee, and then I have some kind of special operator like : : Now this is the get employee method of the employee object. So you have an object, and the object has attributes, which are items of data, and it has methods, which are things it can do. So the code, instead of living in a function with a function name, lives inside an object that might have many functions and methods all tied to one object. And the reason you use that is now you can define other objects that are related to the first object, and they inherit all the methods and properties of their parent object. And that turns out to be a much more useful model of the real complexity of a real business application than the old one where you have to break everything up into functions and variables. So here's the employee class in C++. It contains a first name attribute and a last name, place of birth, and so on. And then it has a thing called getEmp, which gets the information about this employee from someplace, like maybe a database or maybe somebody typing in at the terminal, and it has other methods like hire, promote, fire, put on leave. Various things you might do with an employee are all methods of the employee object. Ruby is also object-oriented, and Ruby is what Metasploit is written in now, I think. It was originally written in something else, but I'm pretty sure it's in Ruby now. It's not projecting very well on my screen there. Let me zoom in. But Ruby looks very much like C++ or Python, and it's very easy to read, actually. So here's an Adobe attack, a stack buffer overflow in Ruby. You have a name for it, and you've got just a lot of comments here, a description of these things. This is an object, initializing it, specifying its info. So it's actually quite easy to write a Metasploit attack. If you get something working, it's pretty easy. You only have to write a few dozen lines of code to translate it into a Metasploit module. It's a simple attack, and a lot of people do. So there are a lot of languages out there. A lot of them are written as jokes. There's lol code. Lol code is based on lolcats. So you use can I have, I'm in your loop, I'm out of your loop, k thanks, bye is what executes a loop, and so on. And then there are esoteric languages written just to confuse you. This is lol code. There's an online lol code interpreter. You can learn how to write things. Visible is what prints things, and so on. And then there's brainfuck. Brainfuck is the most famous esoteric language. Instead of making it easy to program, how could you make it really, really hard to program? And this is brainfuck. Brainfuck is based on the original Turing machine. The entire thing we call computers now started with Alan Turing, and his Turing machine was a bizarre thing that nobody ever actually built, where you would have a line of bits, and you'd have a thing sitting on there like a snail, and it could like change this one bit or move to the right or move to the left. And it would wander back and forth like a snail going down a yardstick and change the bits, and that's all it did, and that's what brainfuck does. And it uses nothing but these 8 punctuation marks. So this increments this moves to the right, this moves to the left, this adds 1 to the current bit, this subtracts 1 from the current bit, this outputs the bit, so this takes input. And so you can write code in this language, and if you do, this is hello world. That prints out hello world. It sits here and adds to this bit enough until it's an H, then it moves to the right, adds enough to make this E, it moves to the right, makes that L, and so on. This is what hello world looks like in brainfuck. And this might seem crazy, but it is actually pretty common to see in CTFs. And this is another kind of evil programming where you make your code hard to read. And this turns out to be very important. For example, it all started probably from people writing web pages. As you may know, the general way you make a beautiful web page is you go find someone else's web page, you right click, take view source, copy it, and then change a couple things and call it your web page. This is how most of them are actually developed. It's technically illegal or something, but in practice, nobody catches you much. And so people got fed up with this, so they started obfuscating their code. They deliberately scramble the code so you can't copy it, block the right click, and then it turns out there's a whole lot of malware written in languages like PHP, and it's obfuscated PHP and obfuscated JavaScript. There's a thing called JSFUG, where you can write JavaScript that consists of nothing but punctuation marks, nothing but curly braces and parentheses and dashes. And it does in this spirit. It's just a CTF I did where there were 64 kilobytes of that stuff, and it added up to like 120 letter flag. And you had to figure out how to fix it because it was broken. But anyway, this is, it turns out that a lot of code is obfuscated. I've done cleanup websites for people who got infected with PHP malware, and the PHP was obfuscated. And it turns out to be a good way to learn how to deobfuscate code. This might seem like just a waste of time, but it's not at all. A lot of what you deal with has been deliberately made hard to read. And if you go into the malware analysis class, we talk more about this. There is a whole category of malware that is compiled in a way so you cannot decompile it. There are a lot of dirty tricks that will confuse your decompiler, like IDA Pro. And one of them just came out about a year ago. Someone wrote a paper and he proved that the move instruction alone is NP complete. So you can compile a source code like C into nothing but move instructions in assembly language and get the job done. It's not the most efficient, but the advantage is it's impossible to read. You cannot understand it. It will just make you cry. And that's what you want if you're a malware author. You want to give someone something and they can't figure out what it does. And so these esoteric languages do have their place in the world of security. They're also good for people learning concepts of programming to just play with it and practice with it. But a lot of bad guys are actually using techniques like that to hide what they do. So anyway, we got another one of these. Cahoots. And then I think there'll be a Hackers Club at noon, eh?
Yeah.
Okay, good. All right. And by the way, somebody told me to check out CTF 365, and it does look very good.
Yeah, that's what
Yeah, I think that was better for beginners. It has nice lessons. I went and finally, I had trouble with connecting to the VPN, but I finally got it working. So,
you sign up for it.
yeah, and I did the first 3 parts. It's good. It's just like 124 homework.
Cool.
Yeah, so I mean, that looks more useful than Hack the Box for beginners. Good, good. I'm glad you're on it. The VPN irritated me, but I finally figured it out yesterday. OpenVPN is nice, but it never works too well. You always have to debug it a bit. All right. All right, I'll wait another 10 seconds. Okay. People are still coming in. I'll wait some more. Okay. 5 more seconds. Okay. 5 questions. So which one of these will not prevent buffer overflow? Okay, GCC is just a compiler. The others are all defenses. All right, which one will allow code injection but prevent its execution? Okay, as DEP sets the NX bit, so even though you inject code and jump to it, it won't run. By the way, I don't think I mentioned how to overcome it. This turns out to be simple. To overcome it, all you do is call the routine that turns off DEP. So fundamentally, you know, how hard can it be? There is a way to reserve memory without DEP turned on. So there's a Microsoft Windows call to turn off DEP. You just have to call it. You know, this is life. I mean, these defenses, there's always a way to get past everything. But it's another thing, and if you don't do that, the defense works. Anyway, so, all right. So which one will allow code injection but make it hard to find? Okay, that's ASLR. That just scrambles things so it's hard to know where you are. All right, which one will detect stack smashing? That's what the canary does. All right. And what language looks like that? That's the one they call BF when they don't want to use bad words. Like I say, I'm glad I teach adults because hacking is closely related to crime and there's a certain amount of bad words involved. So good, I know who these people are. All right, so I've got your points. Okay, so I'm just going to shut this down. I'll stop the share and I'll go up to the lab for a little while and see what's happening there. And I'll be back down here at noon for the hackers meeting. So here goes the share. Okay. End the meeting for all.